All right, so now let's talk about a couple more shaping techniques. So the next one I wanted to mention is about slip casting. So slip casting is named that again. This technique comes from kind of traditional pottery techniques, so very old techniques. Uh, but it's called slip casting because we have a what's called a slip. This is a liquid that has our ceramic powder in it. So this is basically a slurry. And what we do is we take that liquid, that slurry, and put it in a porous mold. And the reason we put it in this porous mold is that this porous mold will remove the liquid from the slurry, leaving behind only the ceramic powder. And it will form that green shape that we want. So you can kind of see that demonstration here. So we have a slip, and then it removes the liquid, and so this darker region is the ceramic compact with the that's had the liquid removed, and then we can take that out, and we're left with this sort of green ceramic. All right. So again, let me sort of walk you through the steps, and I found this kind of nice demonstration of the various steps that have to be undergone to do the slip casting. But the first step is we have to actually prepare the slip or the slurry. And so typically what we try to do is maintain a pretty high solid content. So we want mostly our ceramic powder and not a lot of liquid to have to remove. But we do want to also have low viscosity. So we want it to be free flowing as well. So we don't want it super thick in sort of colloquial terms. So that's the first step. We need to prepare it, and so this is where our additives come in. So we may actually have to add some type of dispersing agent along with the liquid, such that our powder is evenly dispersed and doesn't fall to the bottom. So in the previous section on powder processing and characterization, you'll remember that we talked about sedimentation, and we can use that to determine particle size. Well, we don't want that to happen here. We want the powder to remain in the liquid until the liquid's been removed, and that's the part we want to maintain. So the second step is we have to fill this plaster mold with the slip. And so that's this plaster mold. Plaster is the most common material. It's very porous. And so what that does is basically the porous nature of the plaster acts, it has very small pores and actually kind of acts and has a capillary effect. So what that does is it draws out the liquid into the mold wall. So these arrows kind of represent the liquid coming into the porous pores of the plaster, and leaving behind the particles. And the capillary force effect causes the particles to be packed onto the mold wall. So there's actually an effect that causes the particles to pack quite efficiently on the mold walls of this plaster mold. Okay, so in step 3, this is if we want to make a hollow shape. So we've allowed the liquid to wick into the mold wall, so you can kind of see it happening here. And so that tan color kind of represents the powder that is compacted on the side. So if we want a hollow shape, what we can do is we can drain the rest of the liquid, and we leave behind a thin wall material, like is shown here. And so we still have some slip left over, but that's okay. So we can remove the remaining slip if we want to form a hollow shape. Yeah, so that's basically what this is showing as well. But we can also, if we want to make solid shapes, we can keep adding slip until it is, let me go back. If we don't want a hollow shape, then we can keep adding to form a solid form as well. So this is why it has a good potential to form very complicated shapes, only confined to the plaster mold that we have. And so we can make very complicated shapes, we can make hollow shapes, we can make solid shapes as well. The solid just has the added complication of we have to typically keep adding slip to maintain the level of powder that we need for that shape. And it's going to obviously take longer and longer to dry with the more powder that we have. So this typically is a very good method for making hollow shapes like vases and things you can think of in pottery. Okay, so at that point, the cast is typically allowed to partially dry. So after we've gotten rid of all the slip, we typically let that green ceramic dry in the mold so that we can remove it more easily. And so typically these things are built so that you can take them apart and remove the shape from within. And then after that, after it's taken out of the mold, you typically let it dry even further to get rid of all of the liquid. And then at that point, you can center the part. All right. So another technique that is used is tape casting. And so this is where we start to get into what I would probably say are the more specialized applications. So tape casting is called that because we're forming a tape or a film. And so this is kind of what a typical setup would look like for tape casting. And what this gives us is the ability to form these very uniform films of a ceramic onto a given substrate that we have. So this could be a flexible substrate or tape. It could be something else, but it gives us a thin film on some type of carrier substrate. And so typically these things are quite long tables. And the main portion of it is sort of a conveyor belt, which allows the film, the substrate, to move. And what it does is we have the ceramic slurry. So this is another application where we have to have a liquid version of the ceramic. So we have the ceramic powder in some type of liquid that's dispersed. So you'd have to have typically some type of dispersant agent if it doesn't disperse on its own. And so we have the slurry in this chamber here. And then here we have typically what's called a doctor blade. And so I think I've got an image of it here. Yeah. So we have the slip inside this chamber. And then we have what's called a doctor blade. And so basically what this does is it can be adjusted in height to create that film at a specific thickness. So that controls the thickness of the ceramic. So basically this conveyor belt moves, and so the ceramic is in place, but the film itself moves at a given rate so that we create a thin film on that substrate of the ceramic. So that substrate is then covered in this slurry. And so the rest of the apparatus is typically for drying. And so this whole thing right here you can see is for drying of the slurry so that we have a dried film on the substrate. And so then it can be sintered from there. All right. So another technique that can be used is extrusion. And so extrusion is pretty much like it sounds. We're extruding something through a die. And so in this case, we would have our ceramic in this chamber. We'd have a plunger to push it through this die of a given shape. And then that creates a certain shape. So I put this illustration of Play-Doh up there because that's pretty much what it is. You can see that the Play-Doh has different dies here, and you push it through that die to create a certain cross section, right? And so we can make whatever shape is limited to the die. And so another reason I wanted you to think about this Play-Doh is that Play-Doh is very dough-like and plastic, right? And so extrusion tends to have a very large amount of plasticizers. So ceramic powder by itself is not going to be very plastic. Or even if you add some liquid, it's not going to be very plastic. So we have to add things that will make it very plastic-like for this type of processing mechanism. So that's something that we have to add for extrusion. This is just another operation of this. This one had a plunger. This one has a screw hopper, but they're the same idea. We push the ceramic that's has a lot of plasticizers and potentially binders through a die to give us a certain cross-section shape. So we're constrained here also to the die. So you can imagine you can't make super complex shapes because you're limited in at least one direction by the dimensions of the die and having to push that through. Okay. Another technique, injection molding. This is also, excuse me, this also has similar constraints to the previous extrusion, in that we need to have a very plastic material, because essentially what we're doing here is we have a hopper full of the ceramic, and then again a screw-driven process to move that material into a mold and basically inject it into that mold so that it fills the cavities and gives us the shape that we want. And so these are typically also heat-driven processes. So it typically needs to have a thermoplastic, which gives it that plastic appearance and plastic behavior, so that it fills and moves like a plastic would be. So this process is very similar to injection molding that's done for plastic bottles. And so those materials are thermoplastics and therefore need to be able to heat them so that they can flow freely, and then cool them so they can maintain their shape. So these would have lots of additives that are thermoplastics as binders and plasticizers, so that they can fill this mold just like other thermoplastic injection molding processes. Okay, so I also wanted to mention a couple prototyping type shaping methods. So I will say that this is somewhat dated at this point. There's other methods we can use and that have been that are being researched right now. But if we want to make a very sort of one-off shape, stereolithography, or SLA, is one way that we can do this. And so basically what this does is it takes a resin of a ceramic powder that has a photopolymer. So basically that photopolymer is there so that it reacts to light in such a way. So basically we have a scanning system with a nozzle that has the green ceramic, and then it's inside of this resin. And so basically this resin cures specific parts of the ceramic powder within this photopolymer, and so it'll only cure the parts that are scanned upon, and so we can create a very specific shape in this computer controlled shape. And so this is kind of similar to this is a layer by layer process where we're moving in the z-axis or the z stage. So this is one way. This also might sound familiar to 3D printing. It's very similar to that, and that's where a lot of this is going, as well as ceramic 3D printing. There's also fused deposition modeling, or FDM. This is where we take a ceramic with a thermoplastic and we extrude it through a nozzle in a layer by layer approach, and move the nozzle, and then that is the green ceramic excuse me, that's kind of put layer by layer. So this is kind of like making the icing on a cake. That's basically kind of what that does, and then it sets it after we center this part. So like I mentioned, there's a number of these different sort of prototyping techniques if we want to make a one-off shape, but a lot of the research and various things now are going to 3D printing. So a lot of these techniques have kind of gone in the way of 3D printing. So that's kind of all being encompassed in that area, just specifically with ceramics. Okay, so I want to mention kind of one last thing to this point with forming shapes, and that has to do with porous ceramics. So I think up to this point, I haven't mentioned it specifically, but most of the ceramics we've been talking about are dense ceramics. But I want you to think of applications that would actually require there to be a porous ceramic. So see if you can come up with some applications where it would require a porous ceramic, and then see if you can come up with a way, forming or shaping method that we could actually make these parts porous. So take a minute, pause the video, see if you can come up with some methods, and then we will discuss a couple that I have here in the slides. All right. So now you've had time to take a look at this. Let's discuss a couple of ways that we can do these, and vice versa. Okay. So traditionally, ceramics for the most part are seek to have a high density, but there are applications where we want to have high porosity, so a lot of empty space in that. So it seems a bit counterintuitive, but there are some applications where we do in fact want that. And so there's natural ways to do this, and there's also synthetic ways to do this as well. So pumice is a good example of a natural ceramic that is very porous, and the reason this happens is during the formation of pumice, gases get trapped, and so they can't escape, and so they create these pores. And so you can see that porosity very visible within this material. And so we're trapping those gases that are created during the formation of this ceramic. We can also do that in a similar way synthetically with ceramics. We can add materials like foaming agents that would result in the same way. So when heated, they decompose and allow you to form that porous shape. So this one is with what's called a soap nut slurry, and that basically has a foaming agent that would create gases that end up getting trapped in the structure. You can also, I'm going to go back to the previous slide, you can also add things. So this is an example where we have some type of bead. So like a polymer bead that's available, and we put that in a very ordered structure or disordered structure, whatever we want, and then we put a slurry around it of the ceramic. And so when those beads are heated up, they're going to decompose and they leave behind porosity. And so in this case, we can have a very ordered structure, but it's very porous, right? And so that's another way we can do it. We can add things in like beads or other decomposing materials to create porosity as well. So application wise, what are we looking at? And so a lot of these applications have to do with their sort of unique thermal properties. And so you've probably seen Dr. Beck's space shuttle tile demo. And so that material is very porous. It's made up of ceramic fibers, but for the most part, it has a great degree of porosity. And so one of these tiles, there's a number of components. There's a sort of a black glazing here that's a borosilicate glass. But within that tile, it's very light if you've ever touched one, is a whitish material, and that's the predominant material. And so within that, it's composed of ceramic fibers. And those fibers are typically silica or some other ceramic that are only a few either microns or millimeters in dimension. And they're put in such a way that leaves a lot of porosity around it. So if we just put those fibers together, they're not going to fill space very efficiently. And so most of it, 90% of it, will be air. And so air is a good thermal insulator. And so that is very good for thermal protection in space shuttles and various applications like that. So creating fibers and other materials like that is also another way that we can create these porous materials. So that's not all of the different ways, but that is some of the different ways in which we can make porous materials, keeping in mind that we've talked a lot about dense ceramics, but there's a lot of applications for porous ceramics as well.